This drawing shows a gravitational field. Gravitational field vectors are drawn as arrows that are regularly spaced, showing the force that would be applied to a 1 kilogram object if one were in the field. Now, in order to describe a gravitational field in 2 dimensions, we need a formula that applies to every different point in space. So for that, we're actually going to use a function of 2 variables this time. So the function will work for this point, or any other point in the 2-dimensional plane. To do this, instead of writing g of x, for example, we'll write g of x comma y. And we want to use I hat and j hat notation, or component form would work as well. If we're doing it in component form, we'll just say that our gravitational field never acts in the right or left direction. So we have a 0 for our first coordinate, but it always pulls down with a strength of 9.8. So that's going to be our gravitational field. And this one's kind of an easy one because it's just a constant field. But we could describe fields that are much more complicated, such as the fields around point masses. Okay, so now that we have our field defined, we'd like to turn it into a force. And the way we can turn a field into a force is by multiplying by a mass. Now the mass is going to be, in this case, 10 kilograms. That's our ball here that is going to be rolling from an x of 1 to an x of 4. So let's write an equation for the force that ball will feel. It'll be the mass times g, which is going to be 10 kilograms times our field. And that is going to be 0.98 for this problem. Okay, now that we have our force field defined, what we'd like to do next is we'd like to calculate the work done as our ball moves from one position to the next. And in the past, we had showed how to use the formula F dot delta x for this. Since we're working in 2 dimensions now, we want to generalize it a little bit more so that we can do much more interesting, complicated things with it. Eventually, we can calculate the work done when an object moves in a curved path. So the way we would do this is by using a dot product, actually, but it's going to be a little bit different. In this case, we're going to integrate our force vector that the ball feels, and instead of dotting it with delta x, we'll shrink that down to an infinitesimally small dx. And instead of just putting dx, in this case I'm going to put dr so that it could apply to 2-dimensional situations as well. Now, when we have a dot product of vectors like this, it's a little bit more complicated than just a normal integration along one dimension. What we're going to use here is a line integral, or an integral across any curve of our choice. In this case, it happens to be a straight line, which is kind of an easy one to start with. What we have to do is we have to do a couple things. First, we want to define our force that our object will feel, and we did that. The next thing is we have to figure out where our object is located. Notice that we have dr in our problem, so we need to define what the r position vector of our ball is going to be. Now, one thing that makes this easy is that the work doesn't depend on how fast the ball moves along its path, right? Like that was never part of the work calculation. It was all about how much force was there and how much displacement was there. So we can actually decide the velocity of our ball, and we'll still get the same answer no matter what we choose. So the easiest case here would be to just use a constant velocity of, let's say, 1 unit, 1 meter per second. Normally if we were going to do a problem involving velocity, we would do this, get our velocity function, and then multiply by the time that it takes to get there. And then we would also add in some initial position. Okay. Let's let the velocity function just be 1. So we'll have r of t equals. So we want to think about our velocity though as a vector. We could do it in component form like this, or we could do it in I hat, j hat notation. Okay, that looks like a good position vector to use here. Our object will be starting at the coordinates of 1, 0. And 3 seconds later, it should move to 4, 0. Okay. All right, now if we wanted to write that in vector form, I'm going to do that as well over here. We have r of t equals 1, 0, t plus 1, 0, but an equivalent way of writing this would also be I times t plus 1i, which would give us t plus 1 in the I direction. All right, our next step is we want to figure out the rest of our integral and how to set it up here. So we actually need to find dr, and that can be found by taking the time derivative of the formula that we had just made. So we'll get 1 in the I direction here. That's the velocity, of course. Then we can separate our differentials here, and we'll get 1 I hat dt. Or in other words, dr equals 1, 0 dt. All right, what we'll want to do is take that result that we got here, and we just want to plug it in into the integration. We also want to plug in what we said our force was. All right, so now we can plug in. We want an integral of 0, negative 98. We want to dot that with 1, 0 dt. And we also want to set limits for this. Since we have everything here in constants, we don't have to leave the c there anymore. We can actually go from an initial time to a final time. And so we want to think about the position function that we had made and think about how long it'll take our object to get from its starting point to its ending point. And in this case, we're going to start at time 0. And then 3 seconds later, our object gets to where it was going in the problem. So these limits will work. We want to now actually evaluate the dot product using that formula of multiplying. We want to use that dot product formula of multiplying the first components times each other and then adding in the multiplication of the second components. That formula, if you recall, would be just fx times vx here plus fy times vy. This is actually the velocity there. And we'll go from 0 to 3. Okay, let's plug in. We'll get 0 times 1 plus negative 98 times 0. It takes away the vector nature of our problem here because dot product of two vectors makes a scalar, and that allows us to integrate it. But as you can see, our dot product is just 0. So when we integrate this, we get 0. And this should agree with what we believe the work to be in this situation based on our previous understanding of work. As you can see, our object here moves perpendicular to the force. And when that happens, you got a 90-degree angle between the force that it's going to feel and the direction it's moving. So 0 work gets done. Let's try another one here. And in this case, our object is going to be moving down a hill, so it'll be a little bit more interesting. Let's go ahead and set up what we think our position function will be. All right, so I think that if we were to have this object move, if it were to have a velocity, let's say, of 1 comma negative 1, that would be pretty easy to work with, right? So it would be moving this far each second. So 1 second, 2 seconds, and then after 3 seconds, it's where we need it to be. So that's going to be our velocity multiplied times the time, and then plug in your initial position. It's located at 1 comma 3. So let's put that in as our RI. Okay. Next, we want to take the time derivative of all this to get the velocity. And that is, of course, going to be 1, negative 1, 1, negative 1. Multiply to the other side, and you get 1, negative 1 dt. All right. All right, and also notice that once again we're near Earth's surface here. So our force is going to be just that constant negative 98 J. Okay. Which can also be written as 0 comma negative 98. And we can now plug in. All right, let's see. I think this time I'll write it in vector form just to show the different way of doing it. We would have negative 98 j hat for our force. We want to dot that with I minus j being our velocity here from this. And we need dt to change our differential from dr now to dt. So we'll have initial time of 0, final time of 3. All right, so if we do go ahead and multiply these, we see that the I hat doesn't have anything to combine with. And when you do a dot product, you got to multiply the I hat times the I hat, but there is no I hat over here, which means the horizontal component, that first component would just be 0. So we'll actually get negative 98 times negative 1, which is going to give us positive 98. Okay, and then we want to integrate. We want to integrate that. We'll get 98t from 0 to 3, which is 98 newtons times 3 meters, 294 meters. Okay. Notice here that our object moves to the right and down, but only the downward motion contributes to the work being done by gravity. See, gravity wants to pull it down. The object ends up moving to the right, but that doesn't contribute any work to the situation. The only work that gets done is that 3 meters times the force of the 98 newtons that our object was feeling. So the rightness and leftness of the motion doesn't matter, and that's what the dot product helps us do, because the dot product's all about what part of the motion here is in the direction of the force. Shown here is a derivation of an easy formula that helps us calculate the work done by gravity. The derivation shows that if we just multiply negative m times g times delta y, we can also easily calculate the work done in a uniform gravitational field such as near Earth's surface. Let's see if that's true just by plugging in here real quick. Let's see, we'd get negative 10, which is the mass of our ball, times 9.8 newtons per kilogram. And then we need our delta y. We went from 3 down to 0, so that's a negative 3 meter delta y. And yeah, it comes out to 294 joules. Perfect. I've got one more example here, and this time we'll take a curved path. So this one's going to go in a perfect circle from a coordinate of 1, 0 all the way around a radius of 1 and come back where it started. Now we know that the work done here should be 0. Gravity is going to do negative work as the object is lifted, which means that energy is stored in the field there. Then it's going to do positive work as the object starts to move downward. It'll do some more positive work as it continues to go down in the field. And then once it's lifted back up again, negative work. All this should cancel out to 0. So let's go ahead and see if we can set this one up. Setting up a position vector for it will be a little bit tricky. We have to think about our trig and cosines and sines here. Let's have it move so that its horizontal location, the horizontal component is going to be a cosine of some angle. And I could use theta, but I think in this case I'm just going to use t. Okay, because the speed with which it goes around the circle doesn't matter. And when it comes to the vertical height of my object, I'll make that sine t. Okay, and since the radius is 1, I don't have to worry about that. But basically, my particle would be located at r cos theta in the I hat direction plus r sine theta in the j hat direction. So let's have this and this. Okay. Next, I'm going to need the derivative of this. And let's see, it's going to be negative sine of t I plus cosine of t j. And we want to multiply that by dt. If we want to put it into component form, we'll have this. All right, our force for this problem is going to be similar to before. I just noticed that it's a 1 kilogram particle this time instead of 10, so let's go with negative 9.8 J being our force. So at this point we can go ahead and set up our integral. Alright, we're going to go with negative sine t cos t. Dot that with 0, negative 9.8. Okay, we'll go from t equals 0 to the end of the circle, which in this case would be 2 pi. All right, we want to dot the vectors together. So negative sine t times 0 makes 0. Cosine t times negative 9.8 will make this. All right, bring our integration down. Okay, now we want to find an antiderivative here. Negative 9.8 sine t from 0 to 2 pi. Alright, so this gives us negative 9.8 sine of 2 pi minus negative 9.8 sine of 0. Both of these are 0. So our final result is 0.